All right, today we're going to tackle a really fascinating and, pretty challenging argument from an essay called The Blind Logos. We're going to walk through its main ideas, the evidence it puts on the table, and the conclusion it ultimately reaches. So, let's just dive right in.
So, the essay kicks off in a pretty surprising spot. It actually quotes the famous atheist biologist Richard Dawkins. And this quote, it just perfectly frames the central question. See, everyone agrees that things in nature, especially living things, look like they were designed. The real fight, the real debate, is about how we explain that appearance.
Okay, so if we take a designer out of the equation, how does the standard scientific view explain this incredibly powerful appearance of design? Well, the essay we're looking at introduces a very specific concept to describe that explanation, and honestly, it's central to the entire argument. To get there, though, we need a super quick detour into Greek philosophy. Bear with me. The term logos basically referred to a principle of order, right? A selector that was needed to pick an orderly cosmos out of the infinitely more likely state of just pure chaos. Think of it as whatever force manages to find order in a giant mess.
And this is where the author introduces their own term, the blind logos. This is their name for any mechanism that creates order without having any foresight, without seeing the goal. It works by just trying out a massive number of random possibilities and then having some kind of selection process that just happens to keep the rare successes. The essay directly equates this idea with Darwin's theory of random mutation and natural selection.
Now we get to the real heart of the essay. This is where a massive challenge is thrown down against this whole idea of a blind logos. And to make the point, the author uses a really powerful analogy. So the essay wants you to picture proteins, the absolutely essential building blocks of all life, as being like these incredibly complex combination locks. Just like a lock is made of dials with numbers, a protein is made up of a chain of smaller building blocks called amino acids. Let's start simple. A basic 3-dial bike lock, right? That gives you 1,000 possible combinations. You could probably sit there and guess the right one if you had a bit of time and patience. But check this out. Just by adding 2 more dials to make it a 5-dial lock, the problem gets 100 times harder. You're now staring at 100,000 possibilities. Trying to guess that randomly would take a very, very long time. And then the essay just blows the whole thing out of the water. It calculates that for a pretty short protein, just 150 amino acids long, the number of possible sequences is 10 to the 195th power. That's a 1 followed by 195 zeros. I mean, it's a number so huge, it's almost impossible to even imagine. To put that number into perspective, scientists estimate there are only about 10 to the 80th power atoms in the entire known universe. So the number of possible sequences for just one little protein completely dwarfs the number of atoms in everything we can possibly see. This leads to the author's crucial question. Okay, sure, there's a cosmic number of possibilities, but maybe a whole lot of them work? Is finding a working protein like finding one specific grain of sand on a beach? Or are like half the grains of sand functional? To try and answer this, the essay brings in the experimental work of a microbiologist named Douglas Axe. He actually designed experiments to try and measure this exact ratio. How many of these sequences will actually produce a stable folded protein compared to all the possibilities out there? The results cited from his experiment are, they're pretty staggering. It was estimated that for one of these 150 amino acid chains, only 1 in 10 to the 74th power of sequences will even fold into a stable shape. And according to the argument, that's just the first hurdle. That's not even doing a specific, useful job yet. So here's the bottom line, according to the author. Given these absolutely astronomical odds, a blind random search process simply wouldn't have enough time or enough resources in the entire history of the universe to stumble upon even one of these functional proteins just by chance. So if the blind process is presented as a mathematical dead end, what's the alternative? Well, the author then proposes that a fundamentally different kind of mechanism must be at play. The essay argues that natural selection on its own can't solve this initial problem. Citing Stephen Meyer, it makes the point that selection can only preserve a function after that function is already shown up. This leaves the really hard job, finding the function in the first place, entirely up to a random blind search. And this brings us to the absolute core distinction in the essay's argument. A blind logos, it says, selects after a success is found by pure chance. The proposed alternative, what the author calls a seeing logos, would be a selector that's active during the search, one that's guided by information about the target it's trying to find. So to pull it all together, the essay's conclusion is this: the huge probabilistic hurdles we just talked about can't be overcome by a blind process. Instead, it argues that what's required is a selector that's actually guided by knowledge, a process that can see the goal before it gets there. And for the author, this directly implies a designer. Okay, so the author takes this massive probabilistic problem and blows it up, from the level of tiny cells all the way to the cosmos itself. And this is where it gets really interesting. The author says we see this exact same blind logic on a cosmic scale. Think about the multiverse theory. To explain why our universe seems so perfectly fine-tuned for life, the idea is that there are countless random universes out there, and, we just happen to live in one of the lucky ones. The author argues this is the same move, trying to solve an impossible probability problem by just imagining an infinite number of random tries. It's the same logic, just swapping proteins for entire universes. So after laying out all the problems with a blind selector, the essay offers up its alternative. What if the selector isn't blind? And here's the fundamental difference. The blind logos just picks a winner from random tries after the fact. But a logos that can see, that's a selector that's actually guided by a target during the search. It's not just waiting for a random success, it's actively working towards a functional goal. That's the author's proposed solution to the whole probability problem. Now, to make it clear, this isn't just some fringe idea. The author brings in a heavy hitter, the philosopher Thomas Nagel, who, by the way, is an atheist. And Nagel says, look, these kinds of arguments, they're serious. They're based on empirical data and probability, and they deserve a real answer, not just to be brushed off. The essay wraps up with a really clever Lego analogy. Think about it. When you build something with Legos, you are the seeing logos. You have a goal in mind, and you pick out specific pieces to make it happen. But then the author adds another layer. What about the Legos themselves? The bricks, the system, the way they all snap together perfectly. That was also designed with a purpose. It points to design on an even deeper level. And this brings us to the author's final, pretty provocative claim. They argue that the reason the blind logos idea is so widely accepted isn't because the evidence is overwhelming. Instead, they say it's because it's a philosophical necessity. It's the only option on the table if you want a purely materialistic, non-theistic explanation for life. And so we're left with the essay's big, challenging question. When you really, truly look at the staggering improbability baked into the machinery of life, is a blind, random process enough to explain a world that seems to see? That's the question we're left to ponder.